Hey guys, hope everybody's doing okay. What we're going to do today is take a look at some calorimetry calculations, and these are calculations towards the beginning of our thermodynamics unit involving the transfer of heat and energy and seeing how that process occurs. So let's get started with that, looking at this slide here. Now you may or may not have had a class where we have talked about this slide already, so it may be a repeat, but if it is, you could get a good review of it here, and if it is not a repeat, then it's something to definitely pay attention to. But I have two beakers up here with different substances in them. I have 100 grams of water and I have 100 grams of carbon tetrachloride, CCl4, at the same temperature. So same volume really, or not volume, same mass, and then same temperature. Okay. Does it take up the same amount of energy to heat the contents of each beaker by 1 degree Celsius? So the beaker on the left is water, and I have 100 grams of that. So let's see what it takes to heat that up from 25 to 26 Celsius. It takes 418.4 joules of energy. And if you look at the beaker on the right, we have 100 grams of CCl4. To heat that up by 1 degree Celsius, you have 88.6 joules. So I don't know if you anticipated those numbers being the same or different, but if you anticipated those numbers being different, then obviously you were correct. And there's a reason behind that. This all goes back to the beginning part of the course, really, where we looked at the structures of these various substances, and we look at their intermolecular forces of attraction. So 100 grams of water. The water is primarily held together with hydrogen bonding. That's the primary intermolecular force. And with carbon tetrachloride, CCl4, you should recognize that it's tetrahedral, and it's symmetrical, and it is overall very nonpolar. So the main intermolecular force holding CCl4 molecules together is London dispersion. Okay? So in order to heat up the water, which is held together by hydrogen bonding, you need more energy because those particles are held more tightly together. And remember, kinetic energy is what changes when temperature changes. So to go from 25 to 26 degrees Celsius, that kinetic energy needs to increase. So therefore the particle movement, the speed needs to increase, that velocity needs to increase. So it's harder to get water to increase its particle speed because the attractive forces are so much stronger than in CCl4, where you have your London dispersion forces. It's a weaker force of attraction. Those particles don't need as much energy added to them to get them moving at a faster rate. That's why it's at 88.6 joules. So it's really, really kind of neat how all this comes together from literally unit 1 and 2 at the beginning of the course up through now in our thermodynamics unit. So something to think about as we go through all this. This is something called a heat capacity. The heat capacity is the amount of energy needed to raise the temperature of a sample by 1 degree Celsius. We occasionally use heat capacities, but we're going to look on the next slide at something a little bit more specific. Heat capacity is sometimes difficult to use because it just says the amount of energy needed to raise the temperature of a sample. That sample could be any size. It could be 100 grams, it could be 300 grams, it could be 3,000 grams, right? We want to try to standardize our values a little bit here. So let's take a look at the next slide here where we have the same substance, which is water, but instead of looking at 100 grams of water, we're going to look at 1 gram instead. So how much energy does it take to raise the 1 gram of water to 26 degrees Celsius? Well, we have 1/100th of our sample size. Instead of 100 grams, we have 1. So therefore, our energy required to heat up that 1 gram by 1 degree Celsius should be 1/100th of what it took for the beaker on the left, which is true. So we have 4.184 joules of energy to heat up 1 gram of water by 1 degree Celsius. That is called a specific heat. And that's what we're going to use more often. Okay? The specific heat, the definition of that is the amount of energy needed to raise a 1 gram sample of a substance by 1 degree Celsius. Okay? The symbol in our calculations is going to be a lowercase c for specific heat. And we could tie this into another unit of energy, which is a calorie. So a calorie is the amount of energy needed to raise a 1 gram sample of water by 1 degree Celsius. That's what we did here. We had a 1 gram sample of water. We raised it by 1 degree Celsius. We have 4.184 joules. So therefore, if we ever need to convert between calories and joules or maybe even kilojoules, we can do that because we know that 1 calorie is 4.184 joules. Okay, so The 4.184 is your specific heat for water, and that's equal to 1 calorie. So you always do factor labeling to convert from calories to joules or into kilojoules or back if you needed to for that. So let's see how all this works in terms of calculations and what we need to do here for problems like this. So here's an example for you. It says, how much energy does it take to raise 25 grams of copper from 25 Celsius to 50 Celsius? The equation we're going to use here that we should write down is Q equals mc delta T. Q stands for heat or energy. So let's write this stuff in here to make sure we have it. Okay. So Q, again, stands for heat or energy. M is going to stand for mass. And your delta T is your change in temperature. This is really important, so make sure we write this in here. The change in temperature has to be found the same way all the time. You can't just wing it by looking at your two temperatures. It has to be found by doing T final minus T initial. Okay, so it's your final temperature minus your initial temperature. The consistency there is really important. You'll see as we go through the unit and do some practice FRQs why that is as important as it is. So what do we need to do this? We need something called a specific heat of copper, which is what we have here. So C is your specific heat. Okay, and I defined that on the previous slide, so I didn't want to forget about it here. Specific heat for copper, you just look it up. It's 0.385 joules per gram degree Celsius. So look at the difference here. Water was 4.184 joules per gram degree Celsius. So it took over 4 joules of energy to heat up 1 gram of water by 1 degree Celsius. Look how small it is, or look how small copper's is compared to that. 0.385 joules per gram degree Celsius. Note the units on this are really, really important. So it's joules of energy per 1 gram degree Celsius. So the units have to be included as you do the calculations here so you can see how they cancel, and that's going to give you what energy term you have left. Units are always important, but especially in this unit, kilojoules and joules, it's easy to get them mixed up, or like say, hey, which one are we focus on here for this problem? So you can avoid all that if you follow the basics and include the units in your actual work and the setup that you guys do. All right, let's go ahead and figure this out then. We have Q equals mc delta T. So Q is equal to the mass, which we said was 25 grams, the specific heat capacity for copper, which is C, so that's 0.385 joules per gram degree Celsius, times your change in temperature. So that's T final minus T initial. So it's 50 degrees minus 25 degrees. Okay. So let's take a look at how our units cancel here. We have grams right here on top, so it's 25 grams. We're going to cancel that with the grams here on the bottom in our specific heat. And we have degrees Celsius. If we do 50 degrees Celsius minus 25, we'll get 25 degrees Celsius. So your units of degrees cancels out with degrees Celsius in your denominator. So look what you have left over. You have joules left as your final unit. So if you type it into your calculator, you'll have 25 grams times 0.385 joules per gram degree Celsius times 25 degrees Celsius, and you end up with 2 sig figs, 240 joules of energy in order to do that. So it's really important that this value comes out to be positive because it says in the problem, how much energy does it take to raise a sample, blah, blah. So this is an endothermic process. It's requiring energy. And the Q value, like the sign on that for endothermic reactions or processes, is going to be a positive value. So if you didn't do T final minus T initial, you would get a negative Q value, which looks like energy is released in order for this to happen. That's not true. Energy is required. It's going in. All right. So moving on here, sometimes we have to use something called a calorimeter in order to find out what our either specific heat is, or a change in temperature is, or a mass is, something like that. So how do we measure the amount of energy given off in a chemical reaction? So, when we do Q equals mc delta T, what experiment could we do? We'll do a few labs like this where we'll actually go through this process and do the Q equals MC delta T calculation using the data that we collected in a lab. So the picture on the screen here is of a very, very expensive coffee cup calorimeter, which actually isn't half bad. So what we're going to use in class. You have two styrofoam cups nested together because it's a really good insulator. It's not going to lose a lot of heat or energy. And we're going to have, we might not have the cork stopper and a glass stirrer, but we're just going to use a glass stirring rod. And we have a thermometer that goes into it. So what you can do is you can take the temperature of the water. So that's what we usually have in here. Okay, so here we go. We have some water in here. All right. And we could take it like a piece of metal, like that's hot or cold, and drop it in and see what happens to the temperature. So what would happen is if you dropped a hot piece of metal in here, the hot piece of metal would cool down and the water would heat up. And we could track that delta T. We could track that change in temperature. And then we could figure out how much energy is gained or released based on the mass of the substance that we have and the specific heat value, that M value and the C value in Q equals MC delta T. This can be a little confusing, so I'll try to walk you through this setup here. We have Q reaction, that's what RxN stands for. Q reaction equals negative Q water. And what I mean by that is, like say you took a hot piece of metal and dropped it in here, and I'll show you that in a demonstration in a second. You take a hot piece of metal and drop it in, well, the temperature of the metal is going to decrease, all right? So the temperature of the metal is going to go down. What's the temperature of the water going to do? Well, that's going to go up, right? So what I have here for Q reaction, it's like, it could be a bunch of different things. Say it's the piece of metal you drop in there. Whatever the change in heat is of the metal, like the metal in this case is releasing energy, right? That's the opposite of what the water is doing. The water is gaining the energy, okay? So you could really set it up as Q, you could have MC delta T of the copper, let's say we drop a piece of copper in here. So the MC delta T of the copper is equal to the negative MC delta T of the water. Okay, so we'll go through a practice problem. I'll show you what I mean by this, but it could be a little confusing, but try not to be confused by it, just because if you drop something in a container of water and it's hot, the substance is going to cool off and the water is going to heat up. So one substance loses energy, the other gains it, or one substance gains energy and the other one loses it. All right, let's take a look at a calorimetry simulation that I did for you here, and then we'll wrap it up with a practice problem. All right. Okay, guys, we're going to take a look at a calorimetry demonstration here. So we're going to start by picking a solid, and I'm just going to pick copper because that's the solid that we have in our one of our class examples in our notes that we either did or are going to do. Let's just say we have 25 grams of that. We have a 25-gram piece of copper, and let's say we heat that up to a temperature of 150 degrees Celsius. Okay? I'm going to show the specific heat in joules per gram degree Celsius of copper, which is 0.385. So again, what that specific heat means here is that it takes 0.385 joules of energy to heat up 1 gram of copper by 1 degree Celsius. We're going to combine that with some water. Okay, so we're going to drop it in water and see what happens. So obviously the liquid here is water. Let's say we have 150 milliliters of that. Or 150 grams, which is the same because the density of water is 1 gram per milliliter. The temperature is stuck at 20 Celsius, and the specific heat is something we should know already, 4.184 joules per gram degree Celsius for water. Okay, so one of the common misconceptions students have is they see, and it's the purpose of this simulation, students see 150 Celsius as the initial starting point of your copper temperature. They also see 20 Celsius as the initial starting point of water. And they assume, incorrectly, that the temperature, once you combine the two, will be the average of those, will be in between 150 and 20, which is not going to happen here. All right, so you're not going to, the copper is not going to decrease in temperature by the same amount the water is going to increase in temperature. That is because your specific heats are different. It takes 0.385 joules of energy to heat up 1 gram of copper by 1 degree Celsius and takes 4.184 joules of energy to heat up the water, 1 gram of water by 1 degree Celsius. So you're dropping this really hot copper in here. It takes a lot more joules per gram to heat up the water than it would take for the copper. All right, so the copper is going to heat up and cool down faster than the water is going to. So let's take a look at that. We're going to show the graph here of the temperature of copper and water as the simulation runs. So let's take a look at it. Copper goes in. Okay, copper started at 150. Fast decrease. Look at that. And the water is going to increase, but very slowly. Now, eventually they do reach some equilibrium point, right? And the temperature will end up being the same. So the final temperature is the same. T final is equal for both of these, but it is not halfway between 150 and 20. All right. There you go. Simulation's over. So they do end up at the same temperature. Look at that, 21.96. So the water had an increase in temperature of 1.96 degrees Celsius, and the copper cooled down from 150 all the way down to 21.96. Obviously over 100 and whatever degrees Celsius drop for the copper. Okay, so when we're doing the calorimetry calculations, the delta T, the change in temperature of the copper, is way different than the delta T of the water. Okay, they both end up at the same T final, but they have different initial starting points, as you can see here. Okay, let's take a look at another one real quick. Let's choose aluminum, obviously a common metal. Let's do 25 grams of that. Okay. Temperature, we're going to go up to 150 where we had last time, and now the specific heat of aluminum is 0.903 joules per gram degree Celsius. That means it takes more energy to heat up or cool down a sample of aluminum. So let's see how that impacts our graph over here once we combine it with water like we did in the last one. So let's do 150 grams like we did last time, or 150 milliliters. Temperature is stuck at 20 Celsius, and we have our specific heat of water. Okay, let's run the demo here. Of course, the aluminum is going to cool down a whole lot more than the water increases. Again, we start at 150 for the water, or the aluminum, 20 degrees Celsius for the water. They're not going to meet right in the middle, but let's see what actually does happen. Start the demo. Aluminum goes in. Of course, aluminum drops readily while water increases at a slower, steady rate. And of course, you can see that the lines will eventually meet the same point at some equilibrium. And we end up with, let's see here, looks like 24 point something here. There we go. 24.51 degrees Celsius is our final point. So you can see the aluminum transferred a little bit more energy to the water because our temperature of the water went up a little bit more, right? So it took aluminum, aluminum takes more energy to heat up or cool down, so it was able to transfer a little bit more to the water. And the water's final temperature ended up at 24.51 Celsius compared to when we did it with copper, and the temperature only went up by a tiny bit. And you can see aluminum cooled from 150 down to 24.51. So a really big delta T for aluminum and a smaller delta T for water. Let's do one more here because I want to show you what it looks like for a solution. So let's add a solution of, I don't know, let's just do vinegar. Let's do acetic acid. And let's just do 100 milliliters of that. Let's just do a 1 molar solution. There we go. Okay, look at that. Specific heat of acetic acid is 4.184. Well, that looks familiar, right? 4.184 is the specific heat of water. Well, you have to ask yourself, what is acetic acid? Well, it's primarily water, right? Because it's an aqueous solution. So it's primarily water, so we can say the specific heat is 4.184. And that's usually the case for most solutions. Let's see if we could, let's just add it to, we're limited options here. Let's add it to strong base, sodium hydroxide. Let's do 100 mils, and let's do a 1 molar solution of that. And again, look, 4.184 is your specific heat. So we're adding an acid to a base here. I just want to show you what the graph looks like when this occurs. We have a liquid combining with another liquid. They're of course going to dissolve in one another. We have an acid plus a base. Just look what happens with your lines here. All right, look. is only one line. It's the acetic acid and the sodium hydroxide. So this is an exothermic reaction because the temperature is going up. So it's releasing a lot of energy and your thermometer is picking that up, obviously. And of course, it's going to eventually steady out at the top here. But this is important because if you look, the calculations we would do at this final temperature of 26.61, what we would do with this is, for the calculations, you would combine the masses. Right? I know we have volume here, but we could easily find the mass of each of those. And when you have, this is a solution calorimetry problem. We're going to do hopefully a lab with solution calorimetry. And you'll notice with the calculations, if you have a solute and a solvent, or even in this case, some acid and a base where they create the same homogeneous solution here, you're going to combine the masses, all right? You can see that you track the temperature of the solution as a whole and not a separate line for acetic acid and a separate line for sodium hydroxide like we had previously, all right? So we're going to do a lab that hopefully emphasizes that a little bit. I just wanted to point that out here, that when you have solution calorimetry, you usually combine the masses. And we're going to do a practice problem like that, hopefully in a minute or two here. All right? Okay. So hopefully that simulation helped you understand how we could get the delta T for some of these calculations that we're going to do, and that you could really get a good visual of how one substance heats up while the other one cools down, and you can kind of get a visual of that calorimetry experiment. So let's wrap it up with a problem like this one. It says, what's the specific heat of a 94.5 gram piece of metal that is heated to 80 degrees Celsius, then placed in a 150 milliliter of 21.5 degrees Celsius water if the temperature of the water rises to a peak of 23.5? What metal is it? And you guys have a chart on your note sheet. Okay, it's not on the screen here. So let's make a data table of what we have real quick, because I need to organize my thoughts here. So we're going to look at the piece of metal. So we have a mass of the metal, and the mass of metal is 94.5 grams. We have the specific heat of the metal, which is something I don't know. Okay, the only way to find out what metal it is to find the specific heat and see what it matches up to on your note sheet. And then the delta T of the metal, now this is important, the delta T of the metal is T final, which is 23.5, minus T initial, which is 80. Students always make mistakes on this part. It says, and you're going to say, well, how do you know the final temperature of the metal is 23.5? I know that because look at the problem tells me. It says the water rises to a peak of 23.5 Celsius. Remember the simulation I just did for you. In that simulation, the metal and the water ended up at the same temperature. So your T final, 23.5, the T final is the same for the water as it is for the metal. The T initial is different, okay? Students always make the mistake of this year after year, so hopefully by showing you that simulation, we could avoid it this time around. Let's look at the mass of the water. That is equal to 150 grams. The specific heat of the water, we know that as 4.184 joules per gram degree Celsius. And the change in temperature of the water, again, is T final minus T initial. You have 23.5 degrees minus 21.5 degrees. Remember, your delta T is not going to be the same all the time. Like, it's very rarely going to be the same for both substances. The metal is going to cool off way faster than the water heats up because of that difference in specific heats. Okay? The metal being a lower specific heat, very easy to heat up or cool down. The water with that hydrogen bonding being more difficult to heat up or cool down. All right? So take the time and write out what your delta T is for both of these. And don't just find the delta T of one and pretend it's what the other one is, because that's what students tend to do. And it doesn't make any sense that way. Use the data given to you and easily figure it out. So let's go back to the previous slide and write down what our equation is here. So we have MC delta T for the metal, okay? So this is for the metal over here, is equal to the negative MC delta T for the water. All right, so the metal is cooling down, the water is heating up. Let's see, but the change in energy is the same. okay? The change in temperature isn't, but the change in energy will be, because energy is mass, specific heat, and temperature, all, that relationship between all those things. So let's plug our numbers in. It's really easy to do. So you have your mass of 94.5 grams, your C, which we don't know, so we'll just put specific heat of your metal. Delta T, if you actually figure it out, it's negative 56.5 degrees, equals negative M, which we said was 150, C, which is 4.184 joules per gram degree Celsius, and the delta T here is 2.0. Yeah, 2.0 degrees. Okay. You have to easily do some algebra and solve this. So divide both sides by 94.5, divide both sides by negative 56.5, and you get a Cm equal to 0.24 joules per gram degree Celsius. If you cancel the units out correctly, like your grams on one side and the other side cancel, your degrees on one side, other side cancel, you're left with your specific heat units here, which is what you should have on your specific heat for the metal. So it's 0.24 joules per gram degree Celsius. And if you look on your note sheet there, that matches up best with silver. Oops, S-I-L-V-E-R. Okay, good enough. Silver is what we have here for that one. Okay, so that takes care of, really we did our calorimetry example with just our piece of copper, the Q equals MC delta T. We had the simulation. We can now see what happens when you drop it into water, how we have to compare the Q equals MC delta T for the metal to the Q equals MC delta T of the water and set them equal to each other, but opposite. And now the last thing I want to do actually is one more practice problem with a solution. All right, so this could be a little bit confusing. This is the last one I'll wrap this up with, and then you'll be able to do some practice problems. All right, so you have 15.3 grams of sodium nitrate dissolved in 100 grams of water in a calorimeter. And I think I did one like this in the simulation for you. Temperature of the water dropped from 25 to 21.56 Celsius. Calculate the delta H per mole. So what's the heat loss or the energy lost or gained per mole of the sodium nitrate for the process of dissociation? So the first thing we need to recognize here is the delta H per mole, what the unit is going to be. So that is either kilojoules or joules. Doesn't really matter, doesn't specify here. Joules per mole. That's what we want to figure out here. So I need to do both parts. I need to figure out the joules of energy that either was gained or lost in this process. I also need to figure out the moles of substance that I have. So let's go through and figure that out first. That's easy to do. We have 15.3 grams of sodium nitrate, which is NaNO3. Let's convert that to moles. Molar mass is 85.00 grams in 1 mole. That gives you a mole value of 0.180 moles of NaNO3. So we have the denominator here. I need to figure out my joules. Okay, so let's go ahead and figure that out here. So we have Q equals MC delta T. The key here is the mass, all right? So as soon as you put the sodium nitrate, which is very soluble, in the water, it becomes one homogeneous solution, right? We could say that we have that sodium nitrate aqueous solution now. So the mass is actually a combination of the sodium nitrate and the water. See, it says in bold here, process of dissociation. So that process is what we want to look at here. So typically with solution calorimetry, you will combine the mass of the water and the solute. It's usually what happens. So that's the specific category we're in here, solution calorimetry, because the whole solution is changing temperature. So you put the sodium nitrate in, it dissolves, solution is changing temperature. So it's the combination of those two masses. So your mass is actually 115.3 grams. Your specific heat, most of this is water, right? And I think I mentioned that in the simulation. So we could use the specific heat for that, 4.184 joules per gram degree Celsius. And your delta T is T final, 21.56 degrees, minus T initial, which is 25.00 degrees. Figured out, you get a Q value of negative 1660 joules. Okay, let's think about this real quick. That is what the change in temperature, like that's the change in energy here for this process. Like, we found the temperature of the water. It went from 25 to 21. So the water lost energy. Okay, where did it come from? Where did that loss of energy come from? Like, or where did it go, I should say? It went into that process of dissolving. Okay, so this could get a little tricky here. There's no great way to go about it, but the dissociation process, which is what the problem's asking you about, that took energy to occur. Okay, so it took the energy from where? It took the energy from the water. All right, so the problem's asking you about that process of dissociation. So you have to look at what happened to your temperature change. The temperature change went down. That means it went, like, where did that go? Went into that dissociation process. So the Q for the dissociation is actually equal to positive 1,660 joules. Okay, so the dissociation process was endothermic. It took the energy from the water, which is why our thermometer showed a decrease in temperature there. Okay, so to wrap this up here, let's plug that into our numerator of our delta H value here per mole. So we have 1660 joules over 0.180 moles, and that gives you 9,220 joules per mole. All right. It can be a little tricky here at solution calorimetry. So usually they ask you for the process of dissociation or the solution making process, and it kind of goes back to what we just did, where you have MC delta T equals negative MC delta T. So the Q for the dissociation is equal to the negative Q of what's happening with the water, like solution. You know what I mean? We can talk more about it in class as we go about this, but you can now work on some of the calorimetry practice problems using Q equals MC delta T along with your dissociation or solution calorimetry problems as well. We can talk about them more in class if you have any issues. All right, thanks guys.